In this video, we'll discuss the diagnostic measures that we use to test the assumptions in simple linear regressions. So it's important to realize what the basic questions that we're asking with these diagnostic tests are. First, we'll talk about the line assumptions. So is the relationship linear? And again, for this definition of linear, in simple linear regression, we're just saying, is the relationship between x and y a line? Does the variance change? That is, does the variance get wider or narrower as we go on with the data? Are the errors normally distributed, and are the errors independent? With the model fit category, we're asking, are there any outliers? And are there any important predictors that have been omitted from this particular analysis? So let's dive in. For linearity, linearity is an assumption that is, again, just like it sounds. But when we get to a case where we start to have multiple predictors, which is coming up here in just a couple lectures, then we are going to have a very different definition of linearity. We will talk more about that at that time, but I do want to call that out now so that there isn't confusion when we address this. But for now, you can think of linearity as that there is a line or a linear relationship between x and y. Now, given that we're looking for a linear relationship between x and y, there's a couple ways that we can graphically investigate this assumption. We can create a scatter plot to look at x versus y. So plot y on the y-axis, x on the x-axis, and just look at the relationship between those variables and see is the pattern roughly linear or not. A second plot that we can do is something called a residual plot, and you'll see this again. This plots the residuals, or the e's, versus the predicted values, or y hat. Now, in simple linear regression, you can use x in place of y hat to get the same information, but y hat is going to be a bit of a more general form that we can use in future analyses. For the residuals versus the y hat, this residual plot, we're looking for a random assortment of data that is roughly centered around the line 0, 0. It's a horizontal line down the middle. Now, if the points aren't horizontal, that is, if the middle of the residuals change and go up and down and they don't stay very flat, then that indicates a violation of linearity. And we will investigate this when we start playing with these graphics a bit in R. For independence, independence normally isn't a statistical test. Independence really comes from the method and the sample collection procedures. And that's because what we mean when we say independent is that different data points or cases aren't related in a way that's not included by the model. Some common cases that we talk about where independence is violated is sibling pairs or clusters, classrooms. You know, if we have a whole bunch of students who are in the same classroom, then we shouldn't ignore that. There's something that connects students who are in that same classroom that doesn't connect students who are in different classrooms. So that would be a relationship between cases that isn't in the model potentially. Time order could be a case that if you're standing right next to somebody or you go right after somebody else in a particular task, then the fact that you went right after them means that you and them may have a relationship, that two cases that are very close together in time order might have some kind of relationship. So the goal in independence is just saying there aren't any relationships that aren't accounted for in the model. Now, though there are a couple of different ways we can look at this, such as a sequence plot. However, this is a huge caveat. You can only do this if you have the time variable or if data are given to you in time or order. So if I know that the first data point was measured first, the second data point was measured second, the third data point was measured third, and so on, then we could consider this type of a plot. But if I don't know that, I can't do any tests. I just have to look at the methodology. I have to see if there's any relationships among any of the variables. Actually, another very common one that I didn't mention that happens all the time, now that I think about it, is like a pre-post test, or where we measure the same person over time. If we do that, let's say we have 3 individuals and we measure them at 5 different time points and use that as 15 unique data values, that's not necessarily true. Think also of your dependent samples t-test, where you may have a pre and a post and you're looking at a growth score. You have to treat those as related values, and if you don't, that's where we have a violation of independence. So anyway, for this sequence plot, if I know that my data come in time order, or if I have a time variable to look at, I can plot the outcome by time order, or as we saw in the predictor diagnostic, I could plot the outcome by the predictor, or the predictor by the time diagnostic. I'll say this one more time. Here we're plotting the outcome by time. In the predictor diagnostics, we plotted the predictor by time. Any patterns would indicate a potential lack of independence, so we really don't want to see patterns in these types of plots. But again, I cannot emphasize this enough. If you don't have the time variable, and if you don't know your data come in time order, you can't use this method to assess independence. You have to go back and you have to look at the method. You have to look at the sampling collection procedures. Even if you are able to use this method, you still need to look at the methodology and the sampling collection procedures to see if there are any potential threats to independence. If there are, then you discuss them and you bring them up. But when I'm doing this professionally, I look at how are your data being collected. And given how your data are being collected, that's when we make a conclusion of if we have a threat to independence that we need to account for or not. So I look at the methodology, and that is normally the way that we do this. The sequence plot is a bit of a hack. Normally, we look at the methodology to determine independence. So that's what you'll be expected to look for, is look at the context of your homework problems, and when you're doing project problems, look at how your data were collected for your projects to determine if independence is there or not. So for normality, we can check this in a couple of different ways. Two of the big ones are histograms and QQ or PP plots. These QQ and PP plots are slightly different, but they do virtually exactly the same thing, so we kind of talk about them in the same way. They're also interpreted in pretty much the same way. So in a histogram of residuals, if we assume that the residuals are normally distributed, then if we do a histogram, this should look normally distributed. And we can overlay a normal curve to check if the histogram is roughly normally distributed. We're looking for any evidence of a violation. So sometimes you'll see that it's not perfectly normally distributed, but it's pretty close. That tends to be okay. Histograms are tough to interpret, quite frankly, and actually we have a way better method in these QQ and PP plots. So typically, the very common way of checking normality is a QQ plot. This is far and away the most common method to assess normality. Now what we do in a QQ plot, this is one you may have never heard of before, is we plot the expected versus the normal quantiles. This expected versus normal quantiles should follow a diagonal line. It should follow pretty closely to a diagonal line. So if I'm looking at a plot of these values, the values should line up diagonally in a line from the bottom left to the top right. A nonlinear pattern would indicate a lack of normality. So sometimes you'll see a curve. It'll kind of look like a cubic curve. Sometimes you'll see like a logarithmic curve or an exponential curve. Sometimes you'll see it have what we call lazy S shape, where it kind of almost looks like an S. So any of these patterns would indicate a lack of normality. In a QQ plot, we're looking for it to be pretty close to a diagonal line. And again, we'll demonstrate what a couple of these would look like when we get to our examples in R. The last E stands for equivariance in the line assumptions, or homoscedasticity. So homoscedasticity in the distributional assumptions of epsilon comes from the fact that the sigma squared doesn't have a little sub I in it. That is, the sigma squared in the distribution of the errors does not change for each individual. It is constant across every single I observation. If it had a little sub I, that would mean that it could change for each individual. It doesn't, so it means it's constant across all of the observations. Simply put, this is equivariance, that the variability is the same, or that the kind of the spread of the data doesn't get wider some places and narrower some places. Now this is going to happen a little bit randomly. Homoscedasticity means that in the underlying distribution, this doesn't happen. So we have to get good at figuring out, well, what was just random noise and what is evidence that the underlying distribution might have a different pattern going on. A great place to see this, and probably the best place that we tend to look at this, is that same residual plot that we talked about earlier, plotting the residuals versus the predicted y values, or again, we could plot versus x's in simple linear regression. They tell us the same thing. Patterns are bad, but actually one of the nice things about these plots is they can tell us, based on the type of pattern, maybe what's going on underneath and how we can address it. So actually, if we think about a megaphone shape, what is a megaphone shape? Well, that just means that as y hat increases, the spread also increases. So it kind of looks like a megaphone, something you would shout into. So with that megaphone shape, we would see that there A is a pattern, but B, we would notice the nature of the violation. That is, that as y hat increases, the variability, or the error variance, also increases, and that can suggest solutions. That's what we'll talk about in the next lecture series. All right, so for model fit, outliers are a really, really complex thing, and they shouldn't be. It's just that when we try to write down the rules, looking at the rules of outliers gets more complicated than it actually needs to be. Outliers involve a lot of common sense. Now, in terms of finding outliers, plots are often the best way to find them. So if we just did a scatter plot, we can look at the spread. We can see if any dot is kind of falling out of the main groupings in a scatter plot. And especially in simple linear regression, scatter plots can be the best way to intuitively look at these. The residual plot and the QQ plot can also be helpful in indicating outliers. You'll see a dot that's just far away from everything else, but scatter plots tend to be a really good one. However, this said, some statistics can be helpful in describing what's going on. So we talked earlier about the idea of leverage. There's another concept called influence. So if the different parameter estimates that we're looking at, B0 and B1, which are estimates of beta 0 and beta 1, change quite a bit because of a particular point, then that point has what we call influence. And this is a vocabulary term for outliers. We can come up with things like influence plots to look at the different influence of different points. But influence means that the point actually affects the parameter estimates. Leverage indicates that the point could have drastic effects on the parameter estimates. And typically what this looks like is an extreme x value. And if you think about a lever, if you have a whole bunch of groups of x dots here, and then you have a point way out, it actually functions kind of like a lever, where you can like pull the lever and then all the rest of the points change. It actually does the exact same thing. When you pull the lever off of the main pattern of the main grouping of points, that lever does disproportionately shift the parameter estimates in the prediction line. So that's what we mean by leverage. Leverage tends to be an extreme x value, so that's why we look for outliers in x. Heavy x outliers tend to have extreme leverage. Now, this is only for simple linear regression. When we get into multiple regression, it's not just going to be an x thing. It'll be all of the x variables. It'll be a little more complicated to look at, but this concept and this idea of leverage still maintains the same. Now, what we tend to care about is influential outliers. Like if a point is an outlier, but it tends to follow the pattern, we're not as concerned about it. What we care about is that when an outlier, or a point that's very, very far outside the regular data, does not follow the pattern established by the rest of the data and really drastically shifts our parameter estimates, that's when we start caring about outliers. So in that particular case, that's an incidence where we really need to look in depth at the outlier. We need to make sure that's not a typo. We need to make sure that's not a data entry error. And if it's not a typo, if it's not a data entry error, then we start to study that point specifically to figure out what makes it so different from all of the rest of the data in practical research. Of course, if it is a data entry error, we simply correct the error and refit the model to see if things look better. Now, we can also check for additional predictors. Remember, our assumption is that there aren't any additional predictors in the model. Now, this assumption is related to the assumption of independence. That is, if any additional predictors should be in the model, that is, if there's any part of a particular case or individuals that make them related, or any variable that relates to the outcome, and that's not included in the model, then in some way these cases are related in ways that aren't included in the model, and that affect the outcome. So this is kind of related to independence. It's not exactly the same thing, but they are related. How we approach the idea of checking for additional predictors is we fit our model that we're interested in, and then we take the residuals from that model and we plot the residuals against other potential predictors. And if the residuals and the other potential predictors are just flat, then the other predictors aren't really useful. But if there is a pattern between the residuals and the potential predictor, then that indicates that that predictor probably should be included in the statistical model. Now, as we're talking about other predictors, I feel compelled to bring up something called a type 3 error. Now, this isn't official, and there's actually some debate about what type 3 errors are because there is no official definition. But type 3 errors, tongue-in-cheek, is kind of like getting the right answer to the wrong question. And that comes up when we talk about additional predictors, because when we talk about additional predictors, it's important to realize, are you modeling the right things? Like, is the predictors that you're including in your model actually what you need to be including in your model to answer the research questions? The type 3 error indicates that you can actually create a statistical model that doesn't answer the question at all. So it's important to consider, are my predictors correct? Do I have all of the predictors that I care about in there? And does my model, as I've created it, address the research question? And you do this to avoid the type 3 error where your statistical model that you created doesn't actually address the right question. It's answering the wrong question. So many of the plots that are used actually check several different sets of assumptions at the same time. In fact, what we can do with these particular plots is sometimes we'll look at the plot and we'll kind of assess all of the assumptions at once, because again, some of these plots are useful for more than one thing. So for example, the scatter plot is useful for looking at linearity, but it's also useful for checking for outliers. So when I look at a scatter plot of x versus y, I'm not just going to ignore outliers because I'm checking for linearity at the moment. I'm going to be checking all of my assumptions when I look at each of these plots, or all of the ones that are relevant when I look at each of these plots. Residuals, versus y bar, or y hat, this is the residual plot. I can look for equal variance here, heteroskedasticity or homoskedasticity. Heteroskedasticity means there is unequal variance. Homo means the same, so homoskedasticity means that there is the same variance or equal variance. We have outliers. We can look for outliers. They'll show up on the residual plot, and linearity shows up on the residual plot. So this one has 3 that we can assess. The QQ plot, or the histogram of residuals, shows normality, and it can show outliers. And the sequence plot can show independence across the order of time. So we've got maybe 4 main plots, and I'll say that these 3, again, sequence plot is pretty specialized, but these 3, the scatter plot, the residual plot, and the QQ plot, tend to be run as a group to assess all of our assumptions together, because as a group, they provide evidence for or against the validity of the assumptions of simple linear regression. All right, so what happens if your assumptions fail? What are the consequences that come up? Well, if your assumptions fail, this can affect everything that we have talked about thus far. This affects hypothesis testing. This affects the creation of confidence intervals. This affects the validity of predictions. This affects the validity of parameter estimates. And it affects the validity of all these things in unknown ways. That is, sometimes I'll be asked by a client, oh, well, the assumption failed, so can't we just correct for it or account for it? Well, no. The problem when assumptions fail is that our math literally doesn't add up. The way that in which we make some of our equations equal in theoretical statistics comes from making these statistical assumptions. So it'd be like saying 2 plus 2 equals 4, and then somebody threw a wrench into things, and now we say, well, 2 plus 2 equals x, and we don't really know, or 2y equals x. It's just, there is no longer a correct answer to the problem, because because these assumptions have been violated. So these assumptions were made for a good reason. We will talk in the next lecture set about what we do when these fail. But the consequences when these fail are that we can't just do our interpretations anymore. This impacts all of our interpretations of coefficients and all of their statistical tests and all of the assumptions, specifically with the statistical tests. We just can't trust the statistical tests anymore, or their trust is at least thrown into question. Now, because the assumptions so deeply impact these things, the new order in which we do analysis now is that we will check our assumptions first. Because if the validity of any conclusions that we make is thrown into question if our assumptions don't hold, then first we have to provide evidence, or we have to check our assumptions to make sure there's not evidence against any of these assumptions, and then we can look at interpreting the coefficients. So the very first step now that we're going to be implementing is checking assumptions, and that will happen before we check statistical significance. And remember, we check statistical significance before we moved on to conclusions. So now it goes assumptions, significance, conclusions. Now, if assumptions pass, we proceed as usual. So my assumptions pass. Now I can go on to check my statistical significance and then use that to inform the conclusions that I'm writing. If assumptions fail, we try to fix them if we can. And actually, the process of fixing the statistical assumptions is what the entire next lecture set's about. Now, if the violation isn't too bad, and this is such an important phrase, if the violation isn't too bad. That is, well, it's not normally distributed, but it's not too far away. It's like kind of normally distributed. It's just not perfectly normally distributed. Then we often just continue with the analysis and note that the validity of conclusions may be questionable. I think in a previous video lecture, we talked about the concept of robustness. That was the concept that many of the statistics that we use in this course, though they depend on the assumptions, if the assumptions are violated, minor violations, small violations, or small to medium violations, then the statistics and the validity of their interpretations still hold. That many of the statistics we use are robust to violations of normality and homogeneity variance and that stuff. So if the assumptions are small and can't be easily fixed, then we typically continue with the analysis and make a note. Now, in this class, in your homework, it's a tough thing because in the real world, I'd want you to get used to saying, well, my assumptions are broken, and what we would really do is we would find a different statistical test that doesn't depend on those assumptions. And they're out there. They're a little less common, but they exist. So that's what we do in the real world. In class, because sometimes you can be wrong, you can look at an assumption and say, oh, I think that assumption doesn't hold. And then you stop and you say, well, I can't do anything more. My assumptions didn't hold. Though that's technically correct. In class, I want you to practice writing out the interpretation. So in class, if you have a violation of an assumption, you're going to write that, and then you're going to keep going with the interpretation just in case that violation of the assumption wasn't quite there, so you don't miss out on those points for the interpretation. Now, that's just for class. Again, what happens in the real world is if you violate an assumption, you try to fix it. And you can do that by either using some of the fixing methods that we'll talk about later, or using a different statistical model that doesn't lean on that assumption. And then if you can fix it, great. And if you can't fix it, then you would have to consider how bad the violation is to determine if you could move on with the analysis. There have been cases where the violation of the assumptions has been so bad that we weren't able to continue on with the analysis because we didn't know how the data were distributed and couldn't make any valid claims regarding the data set. It's not very fun. It's not a very fun conversation to have with a client or a boss, I can promise you. All right, now plots versus statistical tests. There are statistical tests of assumptions. Long story short, I prefer plots. Most people tend to prefer graphical methods to investigate assumptions in regression. Part of the reason is because plots describe all of the observed data. And one huge advantage of plots that isn't often talked about, frankly, is that plots can be really helpful in trying to figure out if an assumption is violated. How then do we fix the assumption? I mentioned earlier, this megaphone shape. Well, that might indicate that we need to switch from a normal to a Poisson distribution. But if you're just given a statistic that said, oh, well, this assumption is statistically significantly violated, that doesn't give you any information on what you could do to possibly fix that problem. So having plots gives a ton more information than just raw statistics do. The ASA is kind of frowning on using cutoffs. I think we talked about that in a previous lecture video. So that's another reason that we can avoid that, is plots indicate not just is something normal or is it not normal, but it indicates how bad is it. So in the last slide we just talked about, if it's not too bad, you can probably keep going with it, just with a little side note. But a statistical test, if you're just using like alpha equals 0.05 as a cutoff, you don't get to make that decision. The decision's kind of made for you in that very rough cutoff number, which isn't good for all contexts. And actually, I think we'll display some cases in our R, in working through these in R, in the next video, where we actually demonstrate why this is bad. So in R, we'll play around and we'll show, hey, these are a couple cases where actually this assumption wasn't broken, but the significance test was wrong using its cutoff. The other thing about significance tests is they are highly sample size dependent. So there really is kind of a Goldilocks zone, not too hot, not too cold, where the significance tests function, and if you're comfortable with them, then in that Goldilocks zone they work fine. The problem is that with most statistical methods, it's never a problem to have too much data. Now, it kind of can be in some ways. It's not if you know what you're doing. With significance tests or tests of significance with the assumptions, that can become problematic. If you use like a cutoff of alpha equals 0.05 for statistical significant violation of assumptions. So as the sample size gets bigger and bigger and bigger, the statistical tests for violations of assumptions become so hyper-focused on the distribution of variables that they almost always indicate statistically significant violations of assumptions, even in data sets that really don't have much of a violation if the sample size is large enough. So I remember working with a data set over the summer, working with a client, where this client's data set looked perfectly normally distributed, like it's a textbook example of a normal distribution. You can't tell the difference between a normal distribution and this data set. However, the test of whether the assumption was violated indicated with extreme statistical significance that the assumption was violated, even though you literally couldn't tell the difference between this and a normal distribution. And that was because this individual sample size was extremely large. So when we get large sample sizes, we almost can't use significance tests because they're no longer valid. The other thing is statistical significance tests for assumptions, they don't really work with fancier analyses. Part of that is because the fancier analyses don't necessarily have distributional assumptions that they make. What we look at is much more just general descriptive procedures on the residuals to determine how well model fit is working. It becomes a much looser game, but getting used to interpreting plots early with some of the easier models can help you as you're approaching more advanced models, because you become more used to visually interpreting the validity of assumptions. In practice, though, we use them side by side. What I mean by this is sometimes what I'll do is I'll use the plots, and then if a plot looks kind of borderline, then I might run a statistical test. So that's how I would do it. I would look at the plots first, and then if a plot's kind of borderline, I might run a statistical test. Some people every single time do a plot and a statistical test. If you do that, I would lean on the plot interpretation, especially if they disagree. So if you look at the plot and you think an assumption is violated, and then the statistical test says it isn't, then you're kind of in a bind. But if you look at a plot and the plot looks fine, but the statistic says the assumption's violated, in that case, I would absolutely lean on the plot. So there's definitely some gray areas here, but I'll say that one more time. If the plot indicates a violation and the test doesn't, that's kind of a gray area that you're going to want to think through a little deeper and maybe ask about. If the plot indicates no violation and the statistic indicates a violation, go with the plot interpretation. And of course, if both the statistic and the plot agree, then you're fine. They both agree. What I tend to do practically, one more time, is I tend to run with the plots. And then if a plot is borderline, or I'm not quite sure if that's normal or not, or it looks like it may not quite be the same variance, then what I would do is I would run the statistic to help me make a decision about the plot. So I use the statistic not to make the decision on its own, but I use the statistic to help me interpret the plot. That tends to be a pretty good and healthy way to approach that. All right, so what are the statistical tests that we can use? And we'll talk about, I think we'll talk about one of each of these in the R code when we get to that component. We do not focus on them in this class because, again, the focus in this class is primarily on plots, but I will give you these so that you can Google them. And if you wanted to Google, you would just Google the name of the test in R, and you could find out how to do, I think all of these are built into R or at least available in some kind of a package. Now, it's important to realize, and I should mention this, I apologize for not mentioning this a second ago, but when we're doing a statistical test, we're looking for evidence of a violation. And what this means is that significance implies a violation. And that means that if there is no statistical significance on these tests, there is no violation. So if any of these tests are statistically significant, that indicates a violation of that assumption. And this is a little bit different mentally than what we're used to, but it's important. I'll say it one more time. If there is statistical significance in one of these tests, that indicates a violation. If there's not statistical significance in one of these tests, that doesn't indicate a violation. So for the assumption of linearity, there's no good standard statistical test. We could do something like a runs test. There's a couple other options, but there's not really a great way to approach the linearity assumption using a statistical test. For tests of independence, we could look at something like Durbin-Watson. Now, again, this involves your data being ordered or listed in time order. So if that's the case, then you can utilize this. If that's not the case, then do not use this test. Same thing. If that's not the case, or you don't know that to be the case, do not use the sequence plots. You can only use those if you know that your data are listed in order. For normality, we've got a few different options: the Kolmogorov-Smirnov, the Anderson-Darling, and the Shapiro-Wilk. All of these are options of how you can implement normality testing. Shapiro-Wilkes is probably the most common. Anderson-Darling, I think, is one I can't remember what we use in the R. We use either Anderson-Darling or Shapiro-Wilkes. Kolmogorov-Smirnov is super flexible, but tends to be a little bit old-fashioned. For the equal variance assumption, there's definitely several methods that you can use: the Brown-Forsyth, the Broche-Pagan, and the White test. All of these have advantages in certain areas. I think in the R example, we'll use the Broche-Pagan test. All right. So, view of the future in the next lecture series. Well, first we're going to do our R example, but then we're going to talk about violating assumptions, not if, but when. If you deal with real data, you are going to violate your assumptions. I will say it took me several years through my graduate degree to figure out what to do when I violate assumptions. Like, what do I actually do? I used to just try to pretend that I didn't violate assumptions. I knew that violating assumptions were bad, but I never really talked through what would possibly do when that happens. So in the next lecture set, we will talk about what do you do if and when you end up violating assumptions.